Hello. So I would actually have a quick question before the end of the break. Can I ask it
absolutely.
now?
Yeah, of course.
Okay, so so one of the assumptions that we had for the beginning of the presentation was that variable were IID. While in the very beginning we were speaking about a robotic system where typically the state from the next time step is linked to the previous time step. So could you comment on what kind of bond we can achieve when the distribution is not IID?
Yeah, so that's a great question. So what we're going to do is cheat in the sense that we're going to use as units of independence our trajectories as opposed to individual time stamps. So in that case, in that sense, everything that we're going to do is consistent with this notion of IID-ness, in the sense that we're like each, and I'll make this clear later, but each draw is essentially a trajectory. And so we only need IID-ness across trajectories. That being said, a weakness of our analysis is that we're not able to, because we're treating these things as units of independence, we're not able to like look inside of trajectories and extract extra juice from that. So for example, you would like to be able to say, for example, that if I collected one really long trajectory, I'd be able to get some good information, some good estimates out of that. Our framework can't capture that at this point. And the reason for that is exactly what you raised, which is that in a single trajectory, the individual data points are going to typically be correlated to each other. So you need to be able to handle that in an appropriate way. The way to do that, and there's been some success in doing this, is you need to put more assumptions on the structure of your dynamical system. So for example, in the case where I have a linear system, we actually know how to characterize all of these different notions very, very cleanly and nicely from just a single trajectory. However, in the context of a nonlinear system, work is starting to emerge, but it's a lot harder problem to just characterize what these distributions converge to or look like when they're getting mixed up by a nonlinear system. But like the kind of too long didn't read type summary of what I just said is we're cheating by using trajectories and units of independence. And so what we lose is the ability to characterize that a longer trajectory is also better. In fact, for us, the longer trajectory makes things harder. And if you add additional structure on the dynamical system, there are certain settings where you can actually peer in and look at the statistical properties coming out of a single trajectory, in spite of the fact that the data will, in that case, not be IID at all.
I see. Many thanks.
Yeah, of course. It was a great question. Okay, should we get started?
Yeah, let's do it.
Okay, great. So what I'm going to spend the last hour, 45 minutes, hour and a half on is looking how we can apply these tools to dynamical systems. And the emphasis here is very much going to be on characterizing the effect of stability. And in this case, I mean stability in the dynamical system sense, not the algorithmic stability sense, on the corresponding sample complexity that we have. So the first problem that we're going to look at is the first motivating problem that I introduced at the very beginning, which is we're going to look to try to learn a predictor f hat, such that x of t plus 1 is approximately equal to f hat x of t when my initial condition is drawn according to this distribution. So my setup is I have some nonlinear dynamical system characterized by, I'll call it f star of x of t to disambiguate it from all the other f's that are going to pop up. My initial conditions are going to be drawn from some distribution. This is, again, the only source of randomness that we'll look at. And we're going to make the assumption that our initial conditions are coming from some compact set, so that they're all going to satisfy some norm bound with probability 1 according to this distribution. The problem setup that we're going to study is I'm going to assume that I'm given n IID trajectories. So these are these n different rollouts by generating that are generated by drawing my initial conditions, n of them, from my distribution IID. So I'm using this notation here to denote that I started my initial condition x0, and then this is x1 of c, et cetera, xt of c, evolving under this dynamical system. And I'm just bookkeeping the fact that c was the original initial condition. So actually what I should have is an I there, an I on all of these, right? So these are all, the bookkeeping is the IID CIs. And we're going to look for an F by solving the following empirical risk minimization problem, where I'm going to look for my predictor within some function class. I'm going to look at the empirical mean of some t horizon prediction error. Right. So a typical example, and one that I'll use for most of today, is we're just going to set this to be the 2 norm between x of t plus 1 and my actual prediction. Right. So it's a very vanilla setup, right? I'm just trying to, and this is what folks often do when they're trying to fit models from data. And so we'll take a look at what the statistical generalization properties of this will look like. So as I mentioned before, the 2 steps that we're going to end up having to do over and over again is step 1, I need to show that my loss function is bounded, and then I need to worry about Rademacher complexity. So step 1 is I need to show that this loss function, which I'm just going to use as shorthand for the rolled out prediction error, I need to show that this is bounded for all initial conditions less than B0 and all F in F. So let's impose some regularity assumptions, because we need some notion of regularity or on the underlying system for this to go through. So these are the regularity assumptions that we will impose. One is just as I mentioned earlier, I'm going to have that my initial conditions are drawn from D and from some distribution, and that they're all bounded within some ball. I'm going to also make the assumption that the loss function, this little loss function, is Lipschitz in its 2 arguments. You can kind of generalize this, but this is all we'll need for here. So we'll call that Lipschitz constant of L of Z plus Y. I'm going to assume that this loss function satisfies that property. I'm going to also assume that to start with, I'm just going to assume that my true dynamics are Lipschitz. So I'm going to assume that my true dynamics are less than or equal to in the following way. And an immediate implication of that is a very naive bound without any additional structure, is that I basically just roll out my dynamics to get the following bound that holds almost surely, right? This is just unrolling the dynamics and composing it with F star over and over again. And then finally, we'll define our function class F is equal to the set of F. To begin with, that we're just going to assume that they're Lipschitz. And we're also going to assume that we know that we know the underlying Lipschitz bound for F star, or we have an upper bound on it. We can constrain our functions to satisfy that as well. Okay, so let's look at bounding this loss function. Right, so I have that. Basically, I need to look at the supremum over bounded initial conditions and function classes living in F of the sum over t equals 0 to t minus 1 of L f of x t x t plus 1. Right. So first thing I'm going to do is I'm going to use property 2 to rewrite this as the supremum, and I'm not going to rewrite the arguments, but I can rewrite this as the following way. And I'm not doing anything particularly clever here. I'm actually just kind of going through this as crudely as possible. And just applying the Lipschitz property of F for any F in my function class. I have that this is then less than or equal to right now. If you kind of just if you work through if you unroll the dynamics and kind of collect like terms, this is less than or equal to 2L we're just unrolling dynamics and collecting like terms. You can see that this is an upper bound to that. And so you can pull this out. This is equal to 2LL LF B0 t equals 0 to t minus 1 of LF, right? So then I can bound this. This is actually exactly equal to 2LL LF B0, and this is just a partial sum. So there should be a t there. LFT minus 1 over LF minus 1. And what we're going to assume is that this Lipschitz constant is greater than or equal to 1, because if it's less than 1, then this isn't particularly interesting. So the main takeaway here is that this is going to scale like order up to other constants. It's exponential in the horizon t. And the base of that is the Lipschitz constant. Right? So that's what happens if you don't make any underlying assumptions on the stability properties of the nonlinear system. It's because we can't do anything to we can't do anything intelligent to bound the evolution of the state generated by my dynamical system. And if you think about this intuitively, the way that this manifests itself in the complexity bound, the sample complexity bounds, is what this is saying is that if I have a potentially unstable system, there's a large region that's kind of exponential in t that my trajectories can cover. And so it makes sense that I would need to have more data to be able to efficiently predict over that kind of exponentially blowing up regime of trajectories. So what we're going to want to do is impose stability assumptions so that with time, rather than trajectories diverging, they all converge towards each other. And that will, in some sense, make the space over which we need to reason smaller. So we'll start off by imposing a very strong notion of stability. But it makes the analysis very clean, and then we'll see how to generalize that. So if we assume, we'll assume exponential stability. And what I mean by that for F star, and what I mean by that is that there exists a beta greater than 0 and a decay rate rho in 0, 1, such that we have that x of t is less than or equal to beta rho t x0, which in this case will give us beta b0 rho t. Right, so we're assuming that our state is decaying exponentially to 0 with time. So this is a very strong assumption. And so one thing that was kind of clear from above here is that really the quantity that we need to bound is the sum from t equals 0 to t minus 1 of xt. Right, that's what this is saying. So you can kind of go through all the same exercises to get yourself to this point, and then you have to worry about bounding the sum of x of t from t equals 0 to t minus 1. So I'm just going to focus on what that gives you to see what the corresponding dependency on t will be, and then you can kind of just work backwards to actually get the exact constant. So in that case, if we look at the sum of t equals 0 to t of xt, right, this is now less than or equal to beta b0, sorry, t minus 1, t equals 0 to t minus 1 of rho t, rho to the t. And this I can upper bound now by beta b0 over 1 minus rho, right? If I just let t go off to infinity, this is a converging geometric sum. So the key takeaway here is this is independent of time, of the task horizon, right? So with exponential stability, we get BL is order constant if I'm just keeping track of the dependence on the time horizon. Right, and this is nice, and it kind of makes sense. If things are decaying away exponentially, then there's a certain point after which I don't really need to look at things anymore because they're all the same. They're all basically 0, and that certain point is characterized roughly by this gain of the system. Okay, so now let's look at this is very strong though, and we'll see ways to enforce this later using, for example, Lyapunov certificates. But it's still a fairly strong assumption. You're essentially asking for dynamical system, your nonlinear dynamic system, to be stable in the same way that linear systems are stable, have this exponential convergence rate. So let's relax this a little bit. So for this, I'm just have to briefly introduce or remind you all of the notion of comparison functions. So a class K function, sigma, mapping the positive real line to the positive real line, is continuous, increasing, and satisfies sigma of 0 is equal to 0. So if you've taken a nonlinear control class, if you work through Khalil or something, these are the standard definitions that he introduces. A class K infinity function is class K and unbounded. Right, so as the argument goes to infinity, so does the output of the function. And then finally, we need a class KL function, beta, which maps two positive numbers to a positive number. It satisfies the following properties. One is that if I fix a t and look at it as a function in the first argument, this is class K for all t greater than or equal to 0. And then the second one is if I fix the input to it and I just look at how this changes with time, then this is continuous, decreasing, and tends to 0 for all possible inputs S. Okay. So the reason I'm introducing this is because it allows you to generalize the notion of exponential stability that I defined above, in the sense that we're going to assume now that we have a system that satisfies the following inequality. For beta, a class KL function. Right, so this says that beta gets bigger as my initial condition gets bigger, but it tends to 0 as t goes off to infinity. But it doesn't necessarily have to do this at an exponential rate. So what we end up with then is looking at the bound on our trajectory. This becomes less than or equal to the sum over t equals 0 to t minus 1 of these different class KL functions. Okay, so let's, this is fairly generic. Let's actually fix a structure for the beta, a family of functions, and look at how the corresponding decay rate, the rate at which it converges to t, translates into dependence on the horizon of the function t. So for this case, we'll assume that beta st is equal to some other constant beta. This is just a constant beta tilde greater than 0 times s over 1 plus t to the a for a greater than 0. All right, so this is now decaying as basically 1 over t to some power. And we want to look at how this translates into different bands. So the thing to note is that if we take this expression up here, we can now upper bound that. This then becomes less than or equal to, this will give you beta tilde, b0. So that's the s is the x0, is the norm of x0. So that's always less than b0 times the, times the sum of t equals 0 to t minus 1 of 1 over 1 plus t to the a. Right. So now I can actually upper bound this by I can just take out the first term and then upper bound the rest of the tail with an integral. So I can upper bound this by Give me 1 plus the integral from 0 to t minus 1 of 1 over 1 plus t to the a dt. Okay, so let's look at some what the different cases that come out of here. So if a is not equal to 1, then this ends up being equal to, and I'll spare you the details. You can end up being able to upper bound this by beta tilde of b0 times 1 plus t to the 1 minus a over 1 minus a. And then if a is equal to 1, then this ends up being less than or equal to beta tilde b0 1 plus log t. Okay. So the a equals 1 bound is fairly intuitive, which is saying that if the effect of my initial condition decays like 1 over t, then my horizon will then define scale as order log t. What we need to do now, though, is we need to split this condition up and this first bound up into two settings: one where a is less than 1 and one where a is bigger than 1. So if a is less than 1, so if a is in say 0 to 1, then this whole thing is positive, right? 1 minus a is positive, 1 over 1, and so I can conclude that this is less than or equal to beta tilde b0 of exactly what I have written. And this is basically going to be order t to the 1 minus a in that setting. Now, if a is greater than 1, then what we really need to do is write this as b tilde b0 times 1. The right way to think about this is really 1 minus 1 over t to the a minus 1 times a minus 1. Right, and this is now positive, but this essentially then becomes upper bounded by beta tilde b0. Sorry, there's a tail term that I got rid of. There's also, you end up with a constant. Right, and so this ends up being scaling like order constant, right? Because you can just get rid of that when you're upper bounding it. I'm going a little quickly here, but what this says is the takeaway here is that depending on the convergence rate, A, we get either BL being equal to order 1, order log t, or order t to the 1 minus a. Right, and this corresponds to a greater than 1, that's a equal to 1, and that's a less than 1. Right, so we already see a fairly direct mapping between the underlying stability properties of our dynamical system and the bound on our loss function BL. So what I can summarize this as is what we've shown is that the supremum over initial conditions and functions in F of my big loss function is less than or equal to some expression that depends on T. I'll call it BL of T. And the dependence on T is really determined in a very explicit way by the stability of the underlying dynamical system. Okay, so this is good in the sense that we're now in a position to apply the machinery that we've developed before. So if I define the Rademacher complexity of L composed with F to be this expected value over my initial conditions and the expected value over Rademacher variables of the supremum over F in F of 1 over n times the sum equal I equal 1 to n of sigma I, then this complicated looking expression in the inside here, L of F of X of T of Ci. Right, if I define this, this is the suitable Rademacher complexity that's associated with our loss function. then we can conclude that with probability at least 1 minus delta over my initial conditions, and for all predictors in my function class F, which at this point we've only assumed are Lipschitz, I have that the generalization error, which I'm defining as the difference between the true population risk and the empirical risk, is less than or equal to 2 times this Rademacher complexity that we're going to have to fight with, plus this bound that depends on t, times the statistical rate term that we derived earlier. So we already see very clearly that the underlying stability properties of our dynamical system manifest themselves in this generalization graph. Next, we need to see what happens in the Rademacher complexity set. The Rademacher complexity. Does it also depend on t, and does it depend on t in the same way as BL with t, or does something else happen? So to do this, we're going to have to introduce some additional technical machinery because, as you can see, this is a fairly nasty looking expression, and working directly from the definition is not trivial. So in order to investigate the effects of stability on our Rademacher complexity, what I'm going to have to introduce is a tool known as Dudley's entropy integral. And this is, I'm presenting a very simplified version. And this is mostly based off of material from chapter 5 of Martin Wainwright's book. Okay, so this is going to get a little technical, but stop me if something doesn't make sense. And I'm only introducing this so that you know where these ideas come from. We're not going to actually need the low-level details of these things going forward. So the version of Dudley's entropy integral that we're going to need is we're going to assume that we're given a stochastic process indexed by theta, and theta lives in some index set T. And this index set can be countable, uncountable, it can be just a nasty index set, it can be arbitrary. And we're going to let this denote a zero mean bounded stochastic process. And we're going to associate a metric rho x to it as well. Right? And rho x is basically something that measures the difference between 2 elements, x theta and x tilde. So you can think of this as kind of like the variance, the expected value of the true norm squared of x0 minus x tilde, for example. But we'll leave this as generic for now. Now we're going to define the radius of this stochastic process to be the supremum over theta and theta tilde living in this index set of precisely the metric, right? So really this is kind of the radius or diameter of, actually it's a diameter, the diameter of my stochastic process. Because this is as far away as two elements of this process can be from each other. Now I'm going to define a seemingly esoteric and really going to come out of nowhere definition, but it has some implications that we'll be able to use. I'm going to define the truncated entropy integral, and denoted by J sub d, as the integral from 0 to d of the square root of the log of the covering number of the stochastic process under the metric rho x. And I'm going to integrate the argument u from 0 to infinity. Sorry, from 0 to d, where n of ut rho x is the u covering number of t with respect to the metric rho x. So what's a covering number? Let's just introduce that very quickly. So a set xi, I equal 1 to n, is an epsilon net or epsilon covering of a set x if for all x and x, there exists an xi such that rho of xi less than or equal to epsilon. Right, so this is basically saying that I'm discretizing up my space with this net xi, and then the gap between any point in my space and some discretized point is bounded by epsilon. That's what an epsilon net or epsilon covering is. And so the picture to have in mind is something like, if that's my set, then these are all my different covering numbers, all my different discretization points, and you do this until you fill up the whole set. And what you want to do is then, what the covering number is the smallest such set, the cardinality of the smallest such set, of basically the smallest such epsilon net. Right, so this is essentially a measure of how big my space is relative to this metric, rho x. And it's captured by how finely I need to discretize things to get epsilon accuracy. Okay, so that's the definition, which we need to be able to parse this expression. And so here's the main result. And it says that if all of these things happen, then I can bound the expected value of a supremum over theta tilde and theta in my index set, the deviation between x theta and x theta tilde. So the largest possible deviation, its expected value. This is less than or equal to 16 times this integral. Okay. The 16 doesn't matter depending on what analysis you see, they'll have different numbers. The integral is the important part because we're going to show how this allows us to reduce bounding a Rademacher complexity to bounding the covering number of a set. Right, so I mentioned earlier that we're going to make connections to these different notions. So this is one such example. An important implication of this is you can also get just a one-sided bound in the sense that I can write the supremum over theta in t of theta. This is equal to the expected value of the supremum over theta in t of theta minus some theta 0. The theta zeros are zero mean, right? So I'm just basically adding 0 in here. And then this is clearly less than or equal to the expected value of the supremum over theta tilde in t of theta minus theta tilde. Right, and then that's less than or equal to 16. And the reason we're doing this is we're going to set things up so that my stochastic process here becomes my Rademacher complexity. So let's apply this to Rademacher complexities. I realize that this is going pretty quickly, but it's good to see this at least once. And like I said, the low-level details aren't super important, but just kind of the overall process, because it will inform how we construct these things going forward. So let's apply this to Rademacher complexities. Right, so we're going to define the zero mean random variable z sub f to be equal to 1 over the square root n of this mismatch. Sorry, not this mismatch, but rather this sign flipped empirical sum, right? So again, the sigma i's are IID Rademacher variables. So this is zero mean because I'm sticking those sigma i's in front. Okay. And then we can define a stochastic process in terms of these ZFs. Be our stochastic process. Right, so what we're using to index our variables is the corresponding function f that defines it. That's how we're indexing it, and we're going to assume that f of x is bounded by b for all x and x. And then we're going to define an empirical metric in the following way, where rho x squared of f and g, right? Because we need to define a metric on f, on the function class f, to apply the Dudley's entropy inequality. And I'm going to define this as what I'm going to call the empirical norm squared. And I'm going to denote an empirical norm by the sub n, and that's just equal to the sum over 1 to n of the norm of f of xi minus g of xi all squared. And by our assumption, we immediately have that this is less than or equal to 4b squared. Right? Each of the summons is at most 2b. Okay, so that gives us our diameter d as well. So now if I apply these two inequalities, this tells me that the following holds. I have that my empirical Rademacher complexity of f, that's equal to the expected value with respect to the sigma i's of the supremum over f in f of 1 over n sum over I equal 1 to n sigma I f of xi. Right? But this is equal to exactly 1 over square root n, the expected value of sigma I of the supremum over f in f of my zf. Right? That's how I defined my zf. So I can apply Dudley's entropy integral to conclude that this is less than or equal to 16 over square root n, the integral from 0 to 2b of the square root of log of my covering number of this function class f under the empirical metric du. Okay. So I realize that that's a lot to digest very quickly, but the main takeaway here is the following. We've reduced bounding the empirical Rademacher complexity, and then you'll also notice that there's no x showing up on the right-hand side anymore, so it's actually just bounding the Rademacher complexity itself is reduced to bounding covering numbers. Under this empirical metric that we defined. Okay. So here's an example that you can do with this right away. I'll just state it because it's an interesting connection. So for those of you who know what a VC dimension is, if you can show that the VC dimension of my function class f is equal to nu, then there's a theorem that says you can bound the covering number of this function class with respect to this empirical metric is upper bounded by some constant times nu times 16 times e to the nu b over e to the nu. So in particular, if you throw a log on that, you see that the VC dim of nu implies that my Rademacher complexity is upper bounded by nu over n, up to constant. Right. So for those of you who know what a VC dimension is, this tells you that a finite VC dimension implies a finite Rademacher complexity. Rademacher complexity is actually more general. You can have function classes with infinite VC dim that still have a finite Rademacher complexity. Okay. So the last little bit of technical overhead that we need is we're going to need some properties of covering numbers to be able to tackle our problem. So here's some very useful and I think somewhat intuitive properties of covering numbers. So the first is we're gonna, I'm just gonna state this as a given, but it's not too hard to prove just from like a sphere packing volume argument, which is that the log of the covering number of the Euclidean ball in n dimensions. So I'm going to use b sub 2 of n to denote. Basically, that's a p norm, so that's a 2 norm. It's an n. The ambient dimension is n, and the radius is 1. So we're going to. What I'm saying here is that the covering number of the Euclidean ball in Rn with respect to the Euclidean, the metric induced by the Euclidean norm, is less than or equal to n log 1 plus 2 over epsilon. All right, so this is essentially saying that my covering number is upper bounded by up to constants again, 1 over epsilon to the n. So we have this exponential dependence that kind of makes sense. So you can convince yourself that this makes sense just by making a few pictures. Here's another interesting property that's maybe a little bit less obvious, and we're going to need to rely on it. It's basically, we need to understand what happens when I have a covering number in one space, and then I map that space to another space via a Lipschitz map. So we're going to let f sub theta live in f, and then theta itself lives in its own theta space. And we'll define two norms, a norm on f, which defines a metric on the function class f, and then we'll also have a norm on theta, which defines a metric on this underlying space theta. And then we'll suppose that the map taking theta to f of theta is L theta Lipschitz. Right, i.e. we have that f of theta 1 minus f of theta 2 is less than or equal to L theta 1 minus theta 2. And that's with respect to the appropriate norms. So my claim then is that we have that the covering number of f with respect to its norm is less than or equal to a suitably rescaled, finer gridding of the underlying ambient space, where the gridding is, the rescaling is defined by the Lipschitz constant. So let's see how we go ahead and how we go about prove that. So let's start by just constructing a epsilon over L theta net of the underlying space. So I'm going to pick theta I equals 1 to n theta, where n theta is essentially this covering number up here, be a epsilon over L theta net of theta. Right. So I'm starting off with this finer gridding in the ambient space. And what I'm going to show is that I can use these theta i's to construct a suitable epsilon net in the function space f. Right. So to do that, we're going to need to do a couple of things. We're also going to define the corresponding gridding in the function space f that it induces. Right, so then we need to basically bound the difference from any f in the function space to one of these f sub theta i's. And we need to show that that's less than or equal to epsilon. Right, so then we have for any f in my function space, any f sub theta rather in my function space, we'll let f of theta star, which is going to be in my epsilon net, be such that theta minus theta star is less than or equal to epsilon over L theta. Right, such a theta star always exists by the assumption of the theta sub i's defining an epsilon over L theta net. So now we just need to check that f of theta minus f theta star, right, by our Lipschitz assumption, This is less than or equal to L theta of theta minus theta star. But this is now going to be less than or equal to epsilon over L theta times L theta, which is equal to epsilon, right? So what we've shown is that the covering number for F with respect to its metric is less than or equal to n theta, right? The number, the cardinality of the underlying grid F sub theta I. But this is none other than the covering number of epsilon L over theta of the underlying space. So that's how we get that result. There's another property that we're going to need, and this corresponds to how covering numbers are affected under rescaling. So we looked at what happens to covering numbers when we feed a set through a Lipschitz map. What we're going to look at now is what happens if you rescale things. So what we're going to show is that the covering number of some set in the Euclidean norm is less than or equal to a rescaled version of the covering number of the Euclidean ball, right? And here we're assuming that both theta and B2K1 are subsets of RK. So there's K degrees of freedom in theta. And we're going to assume that the 2 norm of theta is less than or equal to B theta for all possible choices of theta. And the proof is going to go in a very similar way. So I'm going to let xi equal 1 to, I'll call this n2, and that's the covering number of the Euclidean ball, be an epsilon over b theta net of the Euclidean ball in k dimensions. I'm going to define a new net, which I'm going to call z sub I, constructed from the x sub i's just by scaling them out, just by calling them b theta x sub I and 2. And so a couple things to note. First thing is z sub I is equal to b theta x sub I, right? But the x sub I lives in the Euclidean ball, so this is less than or equal to b theta. Right? So this implies then that the net that I just constructed is lies within my original theta, my original space theta. Okay, so now let's choose an arbitrary theta in this space, and note that if I renormalize it by the radius, it's less than or equal to 1, which means that theta over b theta also lives in this Euclidean ball. Now, because we have a nice epsilon net of the Euclidean ball, I'm going to let x star in this original net be such that theta over b theta minus x star is less than or equal to epsilon over b theta. Right? We can always do that by the definition of the x, So what we need to bound now is theta minus b theta x star. And I'm going to claim that this is going to give us the desired bound, because this b theta x star is a member of our set zi. And this is equal to, I'm just going to pull the b theta out, theta over b theta minus x star, and that's less than or equal to b theta times epsilon over b theta, which is equal to epsilon. So we've proved our result. And this is the general recipe for doing these things. It's you construct a net in the lower dimensional or easier to understand space, and then you use that net to construct a suitable net for the thing that you actually care about by feeding it through scaling or a Lipschitz map. We just need to tune the resolution of this underlying thing to compensate for the fact that if I expand something up, if I stretch it out, there's going to be bigger spaces between between the two grids. So I need to rescale it. If I have a Lipschitz map, I need to rescale it according to the Lipschitz properties as well. Okay. We now have the technical tools that we need to bound the Rademacher complexity that we were looking at to begin with. So that's it for the quick detour into Dudley's entropy integral. So back to bounding the Rademacher complexity of our loss function composed with some underlying function class. We're going to fix a function class. Now we're going to consider a parametric function class. And we're going to define it as the set of f theta of x, which we want to make it more explicit, its dependence on theta, such that theta is in Rk, so k degrees of freedom. The norm of theta is less than or equal to b theta, and I'm going to assume as well that f is twice continuously differentiable. So essentially I can take a derivative with respect to x and a derivative with respect to theta, and this is still well behaved. Okay, so now to be able to apply Dudley's entropy integral, we're going to proceed through, our goal is to basically reduce the bounding of the covering number of L composed with F to some bound, some constants times the covering number of the Euclidean ball in k dimensions, because that we have an expression for. So the first step is going to be we're going to want to show that this big loss function is Lipschitz with respect to theta, because then we can apply property 2 from covering numbers that we applied to move from the function class f to just Euclidean space, some theta, which is just a norm ball bound. So the way we're going to do this is we're going to apply the mean value theorem form of Taylor's theorem to write f of x theta 1 minus f of x theta 2, right? We need to show that this thing is well behaved with respect to theta. And we're going to write it as this double integral. So we're going to write it for the integral from 0 to 1. And again, inside the integral from 0 to 1 of the partial derivative of f with respect to x and theta. So this is now a 2 tensor. This maps theta to a matrix that's n by n. And this will give you alpha x, beta theta 1 plus 1 minus beta theta 2. This is being applied to theta 1 minus theta 2 d beta. I'm going to just continue writing down here. And then this will be, we have a d alpha for the other integral, and then we have an x popping out on the side there. This is just an application of the mean value theorem, the Taylor's series, the Taylor's theorem form of the mean value theorem, applying it to first del f by del x and then del squared f del x del theta. It's not too, it's just some algebra, but it's not too hard to deal with. Okay, and then yeah, as I mentioned, this is now a 2 tensor. It takes theta and maps it to an n by n matrix, which is the linearization of f about x. And so we're integrating all of these things together. Oops. To get it bound. So now what we need to do is we're going to assume that xt is less than or equal to some gamma t, with gamma to be d. This is going to depend on the underlying stability properties of my system. And now, of course, we also have that theta is less than or equal to b theta for all theta. So we can define the following constant, which will be the supremum over all x that we'll see and all theta that we'll see of the operator norm of this of the output of this 2 tensor, right? And we're viewing this as a map from RK to matrices that take RK to Rn by n, right? And we're looking at the operator norm, right? So this in particular is going to be the Banach space of n by n real valued matrices equipped with the operator norm. Okay. So this is a constant that you can never really measure or know, but it does exist, and it's going to be bounded by the assumption of twice continuous differentiability. So why did we do all this? So if you wrap a 2 norm around here and then suitably take use the submultiplicative property, you eventually end up with the following bound, which is you can argue that what we've shown is that f of x of theta 1 minus fx theta 2 in 2 norm, that's going to be less than or equal to this constant times theta 1 minus theta 2 times x. Essentially, what this is saying is we're just upper bounding this by the largest gain that you can that it'll spit out, and then you're just bounding this by the norm of theta 1 minus theta 2 and x. So just basically take a worst case approach, a worst case perspective on the integral, and so this gives you this expression. This is important because this is going to allow us to now map the deltas in 2 predictors to the corresponding effect of theta 1 and theta 2 on our loss function. So this is our next step. So now we're going to fix an initial condition x0 equal to c and consider the loss incurred by both f of x theta 1 and f of x theta 2. So for this part, for simplicity, I'm going to assume that my underlying loss function, the stepwise loss function, is just the 2 norm. You can generalize this. You just need that the loss function satisfies a reverse triangle inequality-like property. Okay, so now we write the loss incurred by f of theta 1 minus the loss incurred by f of theta 2. Now, if you expand stuff out and apply the reverse triangle inequality, we get that this is bounded above by the following delta between my 2 predictors. Right. And so this is why we worked hard to get a bound on this expression here. So I can apply that bound to conclude that I end up with something that looks like L delta squared f times theta 1 minus theta 2, the 2 norm. And then we have the sum from t equals 0 to t minus 1 of xt of c times the 2 norm. Okay, so this is nice because now we've reduced bounding the Lipschitz constant of our loss function to bounding the norm of a trajectory of the state of our underlying system. So now we can bring in our stability assumptions to derive bounds on this, right? And so I'm not going to rework this, but I'll just remind ourselves that in the nice case of x of t satisfying this bound, what we end up with then is that we end up with the following expression. So this will then be given by beta b0 over 1 minus rho. I'm bounding the sum there. Right, so this tells me that, and we also have that gamma t in this case is also equal to beta b0, just to kind of highlight that now we can kind of back substitute in these ideas. So this is nice because in this case, then my Lipschitz constant is order 1 relative to the task horizon. Case 2, which is kind of the ugly setting, where all I have is that f star is LF Lipschitz. This gives me that, the sum over t equals 0 to t minus 1 of xt. This will be less than or equal to b0 times LF to the capital T minus 1 over LF minus 1. And this is something that's exponential in our time horizon, which is again consistent with what we saw for BL. And then case 3, we have to kind of split these things up, right? Where I had xt is less than or equal to beta x0 of t, and we gave this a specific form, which was beta x0, which we can bound by, oops, come on, by b0 over 1 plus t to the a. Right, so then this tells me that this is less than or equal to beta tilde b0, 1 plus t1 minus a over 1 minus a for a less than 1. Beta tilde b0 log t 1 plus log t for a greater than 1, sorry, a equal to 1. And then what does it look like? I think it's beta tilde b0 times some constant for a greater than 1, where this constant depends on the value of a. Okay, right. So if you kind of put this all together, right, this is essentially, this is order t1 minus a, this is order log t, and this is order 1 again. So it exactly matches. It exactly matches the dependence that we computed for the bound BL on t as well as a function of the underlying stability properties. So what we can conclude then is that more generally, I have that the loss function this is going to be less than or equal to L del squared f times some constant that depends on t, right? That's these different bounds up here, times theta 1 minus theta 2. And to maybe save myself a little bit of writing, I'm just going to call this L theta of t. So we have that this Lipschitz bound scales with the task horizon in the same way as we previously saw when we put different assumptions on the underlying stability. Okay, so now we can go back to Dudley's. Now we're in a position to apply Dudley's. So we leverage Dudley's entropy integral to conclude that this is going to be less than or equal to 16 over square root n times the integral from 2 to BL of t, the square root of log of our covering number that we defined earlier. Okay, so the first thing that we can do to just kind of make this a little bit easier is I can always replace this upper bound here with infinity. That's clearly going to be an upper bound as well. So what we're going to next apply is property 2, right? Which is that we understand that we have this Lipschitz map. So by applying property 2 of our covering numbers, we have that this is less than or equal to 16 over square root n, 0 to infinity, square root log of n U over L theta now of this set theta in the Euclidean space, right? Because we just showed that the map from the mapping is Lipschitz. That's right. This should be an L sub F. Okay, and then next up, we're going to apply property 3. Right, where we're going to use the fact that theta is bounded to reduce this to a bound over the oh, sorry, I was wondering what I was going to, sorry, I was getting confused because I skipped this step. Okay, so now what we're going to do is we're going to just do a change of variables. Rather, we're going to define epsilon to be U over L theta. This then tells me that du is equal to L theta d epsilon, right? So I can rewrite this as 16 over square root n. Now L theta of t pops out, times the square root from 0 to infinity, square root log of the covering number of just epsilon now of theta the epsilon. Now we apply property 3. Right, which is we're going to use the fact that all of the thetas are bounded by b theta. And then this tells me that I can upper bound this by 16 over square root n, L theta of t, 0 to infinity, log of the covering number of epsilon over b theta now of the Euclidean ball under its own metric, d epsilon. Again, we set epsilon prime equal to epsilon over b theta. This gives me d epsilon is equal to b theta d epsilon prime. So I can rewrite this as L theta of t b theta, the integral from 0 to infinity square root log now n of epsilon b2k1 the epsilon. I just did a change of variables. And now this is kind of our base unit. This is the covering number of a Euclidean ball. Right? So I can rewrite this using the first property. The integral from 0 to infinity, the square root of log of 1 plus 2 over epsilon. Sorry, there's a k that goes there as well. D epsilon. Okay, so now there's an important thing that I actually forgot to do, but I'll do it now, which is note that as soon as epsilon is greater than 1, the covering number becomes 1. You know, if I have a ball that's bigger, if the radius is bigger than the ball I'm trying to cover, then the covering number is automatically 1. Log of 1 is equal to 0. So I can rewrite the upper limit here as, I can just truncate it to 1 because above that it's all going to be 0. And this is equal to 1. Now I can pull out the k, so this will give me now 16 L theta of t b theta square root k over n times this integral from 0 to 1 of log of 1 plus 2 over epsilon to the half d epsilon. You just plug this into a Wolfram alpha or something. This is less than or equal to 1.3526. It's just a number. So if you multiply that by 16, it comes out to like 21 point something, I think. So this ends up being less than or equal to 22 L theta of t b theta square root k over n. Okay. So this is nice. Now we have that the Rademacher complexity is upper bounded by some constant, then times this Lipschitz constant, which scales and varies in terms of its dependence on t with respect to the underlying stability properties of our system, our bound b theta, and then square root the number of free parameters over the number of data points. So let me put this all together so we can just state our theorem, and then I'll kind of discuss some implications of this. So we've now shown that with probability at least 1 minus delta over my initial conditions, and for all f in my function class f, I have that the true loss is less than or equal to the empirical loss, plus, now it's twice the Rademacher complexity, so this would be 44 L theta of t b theta square root k over n, plus our BL, our bound that depends on t, square root log 1 over delta over 2n. Right, now, both gamma of t, no, not gamma of t, sorry, L theta of t and BL of t scale as either order 1, this is exponential, or a greater than 1, as order LF to the t, no assumptions, or order till the see, t1 minus a, this is a less than 1, and order log t if a is equal to 1. Right, so the main takeaway then is you have this parameter that this dependence on the time horizon that varies with the underlying stability properties times square root k over n. That's how these things scale. Okay, so the nice part of this is it makes very transparent the effects of the underlying stability properties of our system on the corresponding generalization and sample complexity bounds. A weakness, and this is kind of what I highlighted earlier, is that our Rademacher complexity bound depends on the number of free parameters in my function class. So this is actually fine, even if you're using, let's say, neural networks, but if you're using something like a shallow multi-layer perceptron or something like that, which is typically what you would use for modeling a dynamical system or for parameterizing a policy or something like that, this usually ends up being okay. We're not in this over-parametrized regime. Where you can oftentimes maybe run into a little bit of trouble is if you start thinking about these ideas in the context of, say, perception-based control, where rather than getting to measure X, I get to see an image and I have to extract the state out of that. In that case, if I have to start relying on kind of convolutional neural networks and stuff like that, then you get into trouble. Then you can kind of enter this over-parametrized regime. That being said, we don't think that this is necessarily fundamental in the sense that this is really just an artifact of our proof technique of going through Dudley's entropy integral and going through these covering numbers. There are other parametric functions. There are other function classes that you can look at where you can actually get away from this dependence on the free parameter and on the number of free parameters. However, we haven't been able to obtain as sharp of an understanding of the underlying stability properties. So, for example, for those of you who know what a reproducing kernel Hilbert space is, which is kind of an infinite dimensional feature space, we can bound the Rademacher complexity there as something that's independent of the underlying number of free parameters because it's infinite. But we end up, even in the best case scenarios here where we have this order 1 dependence, we end up with an order t to the half dependence. So there's kind of a gap there that we're still trying to figure out. Okay. So we have about, I guess, half an hour left or something like that. So what I'm going to try to do is, and I probably won't be able to get through all of it, at least not in the level of detail that I covered this last example, is I want to show you some of the ideas that come up when you try to think about this problem, where you're trying to learn a policy instead of just learn a predictor. Another thing to emphasize, though, is that the prediction map that you learned here, using this to say synthesize a controller is a non-trivial experience because of the fact that if you close a control loop, then the underlying data generating distribution, the kinds of trajectories that you see will be different. So these bounds here will also have to include some notion of distribution shift. And Stephen's going to talk a lot of detail this afternoon when he talks about our imitation learning results, how distribution shift can be mitigated in an imitation learning setting. But I just kind of want to add this caveat here, because this is great for learning predictors, but as soon as you close the loop around these predictors, things get a lot harder. One of the key tools that Stephen's going to use this afternoon and that we're going to have to introduce for this notion of policy optimization is a stronger notion of stability called incremental stability. So let me set up the problem and then we'll kind of see where this pops up and why. So the problem we're going to consider is, I'm going to make this sound fancier than it is, self-supervised, stability constrained policy optimization. So here's our setup. Right, now I have a controlled dynamical system, f of x t ut. Again, my only randomness is coming in through my initial conditions, and we're going to assume that they are less than or equal to some bound almost surely. Our goal is to find a control policy u of t equals pi x of t, such that the risk of a policy pi is equal to the expected value with respect to this distribution of initial conditions of the loss function induced by pi is small. And let me just tell you what we're going to define this loss to be. Here, we're going to keep it really simple today. We're going to just have this be the running sum of the norm of the states evolving under policy pi. So remember, if I have a superscript pi here on the state, that means that I'm rolling out this dynamical system with ut set to pi xt. Okay. Oops. Ooh, running out of battery. Okay. So the way we're going to do this is we're going to go through our empirical risk minimization approach. So we'll define our empirical risk of f to be equal to 1 over n, sum for I equal 1 to n of just these empirical risk, starting from these different initial conditions. Okay, and then we'll define pi hat to be equal to the argmin of pi in some policy class pi of this empirical, oops, this should not be an f, this should be a pi of this empirical risk. Okay, so why am I calling this self-supervised? This is mostly just to make it sound fancier than it really is, but the idea here is that I'm given a bunch of initial conditions. And let's say some pi in pi. We assume access to a simulator returning x0 of pi, which is just equal to the initial condition, x1 of pi of c, all the way to x of t pi of c, right, for all these different initial conditions, I equal 1 to n. Right, and the idea here is that we can self-simulate or self-supervise, self-generate these new rollouts with the current pi that I'm at, and use that to optimize the empirical risk. We are not going to track the complexity of solving this empirical risk problem, in the sense that I'm not going to keep track of, say, the number of repeated rollouts that I need to make over these different initial conditions while solving this empirical risk minimization. That may exceed the number of data points that I have. But I'm just going to assume that I'm actually able to solve this and spit out a policy that optimizes the empirical risk. And then we're going to worry about the generalization gap. Which, as before, is going to be the true risk incurred by the policy minus its empirical risk. Okay, right, and we're going to want to do this for all pi and pi, right? So we're going to do take a uniform convergence approach. Okay, so as before, step one is going to be to bound L C of pi for all initial conditions and all policies pi and pi. Right, so I kind of set this up in a way to make this not too hard to deal with, in the sense that what's this loss equal to? It's equal to exactly the rollout of the norm of the rollout of the trajectories. Right, so we immediately have that are bound, right? This is going to be bounded by some BL of t, where the dependence on t is determined by the stability properties of x of t plus 1 equals f of x t pi x t, which I'll just denote as f pi of x t, closed loop. Right, so specifically, what this says is that if I add the constraint that for all pi and pi, f closed loop pi is stable in the way that we defined earlier, this gives us BL of t that are determined by the stability properties. Right, so this is already suggesting that if you're doing empirical risk minimization to synthesize a policy, it's to your benefit from a generalization perspective to impose constraints so that the resulting closed loops that we see are all stable. Now, we'll talk about how if I don't have time to get to it, Stephen will definitely discuss what comes into play when, what it means to actually impose these stability properties and how do you do it in an efficient way. But we're going to just kind of assume that that's something that we can do. So this suggests solving a constrained empirical risk minimization where you have the additional constraint that f closed loop of pi is stable in any one of the suitable ways that we defined previously. And those will then transfer over to the dependence of the bound on t. So we can already now immediately conclude that with probability at least 1 minus delta over my initial conditions, and for all pi in pi subject to suitable stability constraints, we have that our generalization gap is given by twice the Rademacher complexity of L composed with pi, and I'll define that in a second, plus this bound here. Right, now here, what we're defining is as the Rademacher complexity, the suitable analog to what we had previously. This is given by our expected value over initial conditions, expected value over Rademacher variables, the supremum over pi and pi of this Rademacher flipped empirical loss function. Right, so it's a very natural extension of what we did previously. Okay, so what we need to deal with now is bounding this Rademacher complexity. As before, we'll assume a parametric function class. This will be the set of pi x theta such that, again, theta is norm bounded, lives in Rk, and pi is twice continuously differentiable. Okay. Using very similar arguments, we can show, as we did before, that we can kind of go through the same step, that this map from theta to pi is itself Lipschitz. Right, just as before. This is exactly the same bound. It's just where we're talking about just replace f with pi, and it's exactly the same thing. But now we need to figure out how to bound the Lipschitz constant of the loss function. So let's write this out. Now, just applying triangle inequality as we did, the reverse triangle inequality as we did before. This gives me xt of pi 1 of c minus xt of pi 2 of c. So we need to somehow argue that the map from the policy pi to the trajectory x is also Lipschitz and pi. It's not obvious how to do that in a nice way, given the tools or the stability assumptions that we've made so far. So specifically, what we need is a notion of stability that allow us to bound differences in trajectories. Because that's really what this expression is measuring here. It's a discrepancy between the trajectory induced by pi 1 and the trajectory induced by pi 2. So this notion of stability in trajectory space is something that's called incremental stability. So rather than worrying about stability to the origin, what we're going to worry about instead is that trajectories converge towards each other. So this motivates the introduction of a few new notions, and specifically the notion of incremental gain stability, which is something that we developed recently. So I want to motivate this. So we'll assume a best case underlying stability property, which is just that, for all pi and pi, we'll assume that the sum of the trajectory, the sum of the norm of the trajectory of the points, we're going to assume that this is bounded by order constant, right? So let's assume, for simplicity here, that we're either in the regime where a is greater than 1, or we have an exponential stability. Let's see what this gets us if we don't do anything clever. We'll also assume the following. We'll assume that the map from x to fx pi is LFX Lipschitz for all pi and pi, and that the map from pi to f of x pi is LF pi Lipschitz for all x. And also that pi 1 and pi 2 in pi are L pi Lipschitz and their argument x. Okay, so we're just going to assume that everything is well behaved. So I'll kind of spare you the kind of algebraic exercise of what this implies, but what you can show is that you end up with that x of t of pi 1 of c minus xt of pi 2 of c. This, we can upper bound this by, you have LF pi, and then we'll have this, sorry, that's not right. We can upper bound this rather by the sum of from k equals 0 to t minus 1 of LF pi L pi plus LFX to the t minus 1 minus k times xk pi 1 of c. Right, so you can actually kind of bound this as a function of the underlying state. So what this means then is if I now sum both sides from t equals 0 to t minus 1 of these, this ends up being less than or equal to this expression of wait, I'm sorry, I messed that up. On the outside of this, you also have LF pi L delta square pi times theta 1 minus theta 2. So it's kind of a combination of just rolling up the dynamics and also applying the bound that pi is Lipschitz and in theta 1 and theta 2. So if you put this all together, and this is really the important takeaway, you end up with LF pi L delta squared pi theta 1 minus theta 2. And let me call this whole thing here just L tilde, right, times the sum from t equals 0 to t minus 1, sum over k equals 0 to t minus 1 of L tilde to the t minus 1 minus k times the underlying state trajectory of, say, the first guy. Now, the only meaningful bound that you can kind of extract out of this is by, if you kind of roll out all these different sums and do some counting, you can actually see that this is in fact bounded by the gain of this thing. So this Lipschitz constant, kind of this rollout here, times the sum t equals 0 to t minus 1 of xt, rather t minus 2, xt pi 1. Okay, so why am I going through all of this? Basically, even if this is order 1, without additional stability properties, I end up with something that scales like order L tilde to the t, right? So it's still exponential. So we need something to actually infer or understand how trajectories converge to each other, because just stability on its own doesn't get us far enough. So we need to reason about the stability between trajectories. So there's lots of different ways to do this. So a classic way of doing this is the notion of incremental input to state. Input to state stability. This is known as delta ISS as a shorthand, right? And so a function that satisfies this notion of stability, rather if you consider a dynamical system given by f of xt ut, and we're going to let phi t of c and some input signal denote the state at time t evolving under signal ut from initial condition x0 equals c. So it's just a little bit of extra bookkeeping here. We need to kind of keep track of the input signal. Then f is delta ISS if there exists a class KL function beta and class K infinity function gamma, such that for all pairs of initial conditions and all input signals living in some space, and for all t greater than or equal to 0, I can bound the difference between one signal, one trajectory that's starting at initial condition C1 and that's being perturbed by this input ut minus the other trajectory, but it's not being perturbed. I need to be able to bound this by my class KL function as a function of the difference of my initial conditions and t, plus this gamma function, this class KL function acting on the largest input that I've seen so far. So this is a stronger notion of stability, and this allows us to improve our bound. Okay, so if I assume that f of x pi 2 of x is delta ISS, and note that x of t plus 1 evolving under pi 1 is equal to f of x pi 1t pi 2. This is all evolving under pi 1 plus delta pi 1 pi 2 applied to x of t pi 1, where delta pi 1 pi 2 of x is just equal to f of x pi 1 of x minus f of x pi 2 of x. Right. So what I'm doing here is I'm taking the policy, the trajectory under evolving under the policy pi 1 and rewriting it as if it were evolving under policy pi 2 plus some perturbation term, and the perturbation term captures this gap between the two closed loop systems. Then we can apply, we can actually use the ideas of incremental input to state stability to get a better bound, right? So notice that we immediately have that delta pi 1 pi 2 of x is less than or equal to LF pi 1 of x minus pi 2 of x, and that's less than or equal to LF pi this partial theta 1 minus theta 2 times x, right? Just kind of putting everything together. But this is nice now though, because I can now look at my loss function, the difference between my loss functions, pi 1 and pi 2, right? And then that's less than or equal to these, the discrepancy between these two trajectories. And now I can immediately apply my delta ISS bound. They're both starting from the same initial condition. So the only term that pops up is this. And I'm going to define UK to be exactly this delta term. Right? So this immediately gives me that this is less than or equal to sum of t equals 0 to t minus 1 of gamma times the max over t minus 1 of this bound, right? Delta pi 1 pi 2 of now xk under pi 1 of c. Okay, so this is nice. I'm going to do a couple of things, which is I'm going to, in one shot, I'm going to introduce this bound, and I'm going to replace the max with a sum over all of the elements. So I'm going to upper bound it in that way. So this immediately gives me that this is less than or equal to gamma applied to LF pi L del squared pi times theta 1 minus theta 2 times the sum over k equals 0 to t minus 1 xk of pi 1. Okay, so this already, you'll notice that what's in the I can upper bound what's in the sum in here. I can replace the little t minus 1 by a t minus 1. Right. So now what's inside of this doesn't depend on little t anymore. So this is immediately less than or equal to t. times gamma of all this stuff. L squared pi, theta 1 minus theta 2. And let's assume that this is order constant, right? We're going to assume, again, we're in this nice regime where this is order constant. Okay, so I have this gamma function. And now if I don't know, if I assume some, let's say, homogeneity property to the gamma function, then gamma, let's assume that gamma of A is less than or equal to A to some constant, right? Then I can bound this by then I'll have T, LF pi, L del squared pi, that to the C. Now I can take B theta and pull out C minus 1 of those. Theta 1 minus theta 2. Okay, so all of this to show is that we're able to improve to get order T dependence. Right, so as opposed to having this exponential dependence, we end up with order T dependence. That being said, what this shows is that we need more resolution into how signals map from one to the other. So this is what motivated the definition of this notion of incremental gain stability. Or what we call IGS. So it's the same setup as before, as the delta ISS definition. And now this is going to get a little cumbersome, but bear with me. Now we're going to let A0, A1, B0, B1 be constants that are greater than 1. And zeta and gamma are just constants that are greater than 0. Actually, we're going to, without loss of generality, we're going to assume that they're greater than or equal to 1. We'll also assume that A0 is less than or equal to A1, and B0 is less than or equal to B1. Then we say that I let phi just collect all of these, be the tuple of all of these different parameters. And F is then this C incremental gain stable. If for all horizons, for all T that are positive integers, all pairs of initial conditions C1 and C2, and for all input sequences, for a subset of some space, we have the following. We have that the sum from T equals 0 to T minus 1, or let's do it to T, of the minimum between the norm of my discrepancy to the power of either the smallest term A or A0, and delta T to the power of the maximum of A and A1. This has to be less than or equal to my gain zeta times the discrepancy between my two initial conditions raised to the power A, plus gamma times the sum of T equals 0 to T minus 1, the max of UT either raised to B0 or UT raised to B1. Okay, and here, delta T is equal to this discrepancy term of the forced system starting from initial condition C1 and the unforced system starting from initial condition C2. Okay, this is a nasty looking definition. So let's parse it a little bit, and then I'll quickly kind of give you some implications of this. The idea here is this is essentially bounding the gain from a signal U and say some discrepancy between initial conditions. the bound from the signal u to the discrepancy signal. And we're doing it in kind of, you can think of it as kind of a generalization of an LP to L cube gain. The reason that we have these weird mins and maxes everywhere is because if you have a system that isn't exponentially contracting, then there's a phase transition that happens about the unit circle. So as a concrete example, if something is converging at a rate, let's say x cubed, outside of the unit circle, x cubed is converging very, very, very quickly. Then once you get inside the unit circle, x cubed is actually a lot smaller than x. So it starts converging very, very slowly within the unit circle. And that's what these mins and maxes are characterizing. So on the left-hand side here, we're bounding the slowest converging of these different entities. And on the right-hand side here, we're picking out the worst case u, the larger u. So if u is less than 1, it would be b0. And if u is greater than 1, it'd be b1. So that's the intuition here. That's why we have all these annoying mins and maxes. We tried really hard to get rid of them, but you really actually need them.
May I ask a question?
Yeah, please.
How does this relate to, say, the contracting dynamical systems, like the incremental exponential stability?
That's a great question. So what I'm hoping to have time to show quickly is that contraction implies delta ISS. IGS. And in particular, A0, A1, B0, and B1 are all equal to 1. So this collapses down to something. So exponentially incremental stable systems imply IGS with those parameter choices, but not necessarily the other way around. This is a strictly weaker notion than exponential incremental stability.
Yeah, thank you.
Yeah, sure. So yeah, why don't I, I don't think that we're going to have time to get much beyond this. So why don't I, instead of trying to rush through everything, why don't I just spend 1 or 2 minutes, we've only got 2 or 3 minutes. Stephen is going to talk a lot more about incremental gain stability this afternoon. But maybe what I can do is just jump to I was a little maybe over ambitious, but I'll just jump to the final bound, which is using these ideas of stability. We can bound, and actually what I can do is I'll write up the notes, the additional notes before I share this with you guys, so you'll still have access to it. We can bound the Rademacher complexity of this composition as 1 over 32, what I'm going to call gamma 1 of t, the square root of a over b, square root of k over n. Where here gamma 1 of t is gamma 1 of t scales like t to the 1 minus 1 over a1 times 1 plus b over a. So what does this mean? Just very quickly, and you can also show that the BL of t, when viewed through this lens, scales as order t to the 1 minus 1 over a1. So an immediate implication is that if I have a contracting exponential system, a1 is equal to 1, so the temporal dependence drops away, because the power is always equal to 0. Stephen's going to show you an example of a system where we actually end up with the C parameters are equal to 1, 1, 1 plus P, 1, and 1, and some other stuff for any P in 0 to infinity. And so this allows us to really tune the underlying stability of the underlying dynamical system. And this is manifest exactly in this bound here in a very transparent way, in the sense that this would lead to a gamma 1 of t that scales as, this would be order t to the 2p over 1 plus p, and BL of t would scale as order t to the, I think it's just p over 1 plus p. right? So again, this shows a very, very transparent and fine-grained mapping between the underlying stability of the dynamical system and the corresponding generalization guarantees that you're able to extract. So the big takeaway here is that the reason we introduced this somewhat aggressive and convoluted definition is that it provides the level of resolution needed to be able to extract out the convergence rates of trajectories towards each other in a meaningful way, so that we can go beyond exponentially, for example, exponentially contracting incrementally stable systems. Okay, so you know what, I'll end it there and see if there are any questions. And what Stephen's going to do this afternoon is he's going to build up off of these ideas and show how they can be applied to learn stability certificates from data, how you can reason about stability constrained imitation learning and really deal with distribution shifts induced by changing your policy. And he'll also talk about regret bounds for nonlinear adaptive control. And the kind of key underlying tool in all of these that makes this doable and tractable is some underlying notion of stability in trajectory space. And at a high level, this makes sense. Our units of independence are these trajectories. So if we can argue that trajectories as they get longer look more and more similar to each other, then our dependence on the horizon task will reflect that if you do things in the right way. And that's really what we were working hard to show here, was to show that you can really, in a fine-grained way, translate the underlying stability properties to the suitable generalization bounds. All right, I've been talking for 4 hours, so I'll leave it now and see if there are any questions.
I actually have one question.
Please.
So my question is, we have seen a lot of upper bounds, and my question is whether there exist some lower bounds as well. Like, I mean, you said that different upper bounds exist, and they describe, I mean, the different stability properties, and I'm wondering whether they're like tight or.
That's a great question. We don't have any lower bounds for any of these right now. I mean, for uniform convergence, you'll always have the 1 over square root n dependence is tight, but all the other constants and the dependence on t and all those other things, we don't have corresponding lower bounds right now. I think that's a really interesting question to look at. And I think, again, that if you go through something like a Kramer-Rowe bound or a Swad's method or Fano inequality, these notions of covering numbers are going to come up again. And if you have stability in this space of trajectories, then the covering number should somehow be well behaved. And so I expect that you might be able to get, there may be a path forward to get lower bounds here, but you'd also probably have to potentially put more structure on the underlying system to be able to say anything meaningful. But it's not something we've looked at, but something that we definitely want to look at.
Thanks.
Yeah, sure. That's a great question.
Sorry if I could ask another question.
Please.
So for most of the lecture today, we've talked about effectively flow maps of dynamical systems, where you start at a state and the output of your unknown function is the next state after some time step. Have you ever looked at just staying at the ODE level, where your unknown function is actually your x dot equals f of x, your f there is unknown? Is there still is there still like a way to use this theory, or is it like is that just extremely complicated?
Right, that's a great question. So here's what I can tell you that I'm sure is correct. So what Stephen's going to discuss this afternoon in terms of learning stability certificates, there's really no difference between whether the underlying dynamical system is described in continuous time or discrete time. But the kinds of bounds that we're able to provide are relative to a discrete sampling of a given trajectory. So if you're operating in continuous time, we're still going to assume that there's some sampling process that happens, so you end up with a capital T collection of points. And then we can give you guarantees in that space. I think it's a really interesting question, and we haven't thought about it yet. And I certainly haven't thought about it rigorously. And say, for example, the first example where we're looking about prediction maps. What happens if you actually try to operate at the ODE level and try to do something that doesn't discretize or sample along a trajectory? I haven't really thought about that. I think that could be a really interesting direction to look at as well. And if you're able to do that, then you can bring in all the fancy new deep learning stuff on neural ODEs and all that as well. And so maybe get a NeurIPS paper out of it.
All right, thank you very much.
Yeah, thanks.
Hi, I have a question, like regarding the application of these bounds, because from now what you give, you actually use a lot of this big O notation, but actually when you really want to apply this, like you want to get some satisfactory results, you also you have a very limited resources. So you are actually care about the big constant that.
Great.
Yeah.
Great.
So
yeah. Go ahead.
I don't know how you can comment on the tightness or the application, how you avoid being too pessimistic when you really apply this result.
Yeah, that's a great question. And I'm using this big O notation, but a lot of it was to save time in the sense that it's completely possible to keep track of all the explicit constants and all of that. And the good news is that the explicit constants aren't terrible in the sense that the biggest one is kind of like what we have on the screen here. It's like on the order of 100. That's the good news. The bad news is that these bounds are still super loose and super conservative. That's a feature of uniform convergence in the sense that when you're using these kind of statistical convergence guarantees, you're always kind of overly pessimistic because you have to worry about every single possible function. So there's two ways to think about this. One is that the benefits of these bounds are less so in giving you an explicit upper bound on your generalization error, and more about giving you an understanding of how the underlying stability properties of, say, a dynamical system can make your learning task easier or harder, right? So what we've shown here is that the stability properties of an underlying dynamical system translate very explicitly to the dependence on T of these upper bounds. So a more stable system is provably easier to learn. Now, if you want to try to think about things in practice, and Stephen's actually going to comment on this again as well this afternoon, there's a few things to think about. One is everything that I've been thinking about here, you can look at it as kind of it's viewed through the PAC framework, the probably approximately correct framework. There's recently been some work showing that if you instead of use the PAC framework for generalization, you use something called PAC Bayes, the actual constants, the upper bounds that you get are actually practically useful. They're quite tight. There are some additional difficulties that come into that because you have to optimize both your loss and a suitable KL divergence measure between your training and test time distributions. So it's a little bit of a delicate dance, but Ani Majumdar at Princeton has used these ideas to great success in the context of some learning and imitation learning type settings. Another way to do this is, at least in other, what you might want to do is instead of using these analytic bounds, you could use something like the statistical bootstrap, where you simulate a bunch of true and empirical risks, and you bound the difference between the two of them. And there are certain guarantees that allow you to I don't know if they've actually been ported over to empirical risk minimization, but bootstrapping in general ends up giving you much tighter bounds than this. They're just not going to be really analytic. You're going to have to just simulate stuff. But the overall point that you raise is a fantastic one, which is, what are these bounds good for? Right, and I didn't emphasize this enough. These bounds are really not meant to be used as, okay, I literally need to collect n greater than or equal to 132 squared gamma 1 squared AB over K or something to get an epsilon over epsilon squared accuracy. That's really not the way to look at these bounds. The way to look at these bounds is more to be able to understand what the underlying properties of a system, how they manifest themselves in the easiness or difficulty of a learning task. And that's really what we were after here.
Okay, thanks a lot. That's a very clear explanation. Thanks.
Sure.
Can I ask a question?
Yes, please.
I read in a paper the incremental stability is proved by leveraging the remaining energy. So could you comment on this, the difference between the derivation here?
Yeah, so I didn't have time to get to this, but Stephen will get to it later. So the way that you can, a way to certify this, this property of incremental gain stability, it can be certified via a suitable incremental Lyapunov function. So a Lyapunov function that measures changes in x minus y, for example. And what you can show is that, you know, for contraction metrics, if you kind of start off by using the underlying Riemannian metric as your Lyapunov function, you can actually show that it satisfies this this definition, or that rather the Lyapunov certificate definition that we have with all of these constants set to 1. So kind of a way of summarizing this is that for contraction, you really want to use the Riemannian metric as your contraction metric. We can take that contraction metric and use it to construct a suitable Lyapunov certificate of this notion of incremental gain stability. Then we can also generalize beyond that, since we can relax the different constants A0, A1, B0, B1 to be larger than 1. And there are corresponding suitable Lyapunov certificates that enforce that potentially don't depend on an underlying Riemannian metric. Really, what we were motivated by here was we were trying to see what happens if you relax exponential incremental stability, this contraction. If you relax it to something that instead of converging exponentially, converges polynomially, what do the resulting bounds look like? And so that's what motivated this definition.
Thank you.
I have a question. So we assumed throughout like Lipschitz continuity assumptions about the dynamics and the loss. So like the loss seems pretty fundamental, like to get through the contraction argument of the Rademacher complexity. But I was wondering if like you can become less restrictive with the dynamics at least. Do we need Lipschitz through all of these arguments, or is that's a great?
No, that's a great question, right? So the Lipschitz stuff that I imposed was really about I needed that just to mostly just be able to derive the naive bounds. You could imagine that if I have some function f, some dynamics f that perhaps aren't Lipschitz, but instead still satisfy this notion of incremental gain stability. So say I have a hybrid system that has continuous flows and discrete jumps, but whether it's flowing continuously or doing these discrete jumps, these inequalities are still valid, then you can basically push everything through. But yes, I mean, so that's a great question. Another interesting thing to think about is, what's the right way to model dynamical systems that are hybrid in nature? What's the right underlying function class to use? And there's been a lot of really interesting work going on and thinking about how do you parameterize, say, contact dynamics, which really captures one of these issues in a way that you still actually preserve smoothness and Lipschitz continuity in the underlying parametrization space, even though you're capturing a discontinuous phenomena. So again, it's a fantastic question, and I think it's something that we can address. We haven't looked at it explicitly, but there's nothing stopping us from considering function classes that aren't necessarily Lipschitz, that still satisfy this notion of stability.
Okay, that's interesting. Thank you.
Yeah, of course. Thanks for the question.
Are there any more questions?
Okay.
It seems not to be the That seems not to be the case. So then, thanks everybody for participating, for the questions, and especially, of course, Nikolai, for the fantastic lecture. So
appreciate that. Thanks, folks. Thanks for being so engaged and asking all those questions. I hope that you found this useful.
Yeah, I think everybody, at least we learned a lot. So thank you very much. It was fantastic.
Awesome.
And I hope to see, of course, many of you in about 45, yeah, in about 45 minutes again at this place. So
Awesome. Thanks, folks.
have a great day, or great break.
Cheers. Have a good rest of your evening. I guess. See ya.